In this video, we're going to focus on the 555 and the internal comparators therein. We'll have a look at the fact that these form a window comparator, and we'll take a precise look at how they work. You can see here, this is a circuit diagram I've set up in TAFE, and in the second part of this video, we'll go on and explore what's happening with the LM358 and the LM339 at the end. However, for today's video, all we're interested in is the 555 and the 557A, the transistor, P&P transistor here. So let's move on and have a look at some of these things. Just here again, this is part 2 of the video, so a bit of a preview there at what part 2 is going to be looking like. Again, that'll happen very shortly, but today let's go on and we're just going to concentrate on the 555. So here we are, Sawtooth generator for the op-amp PWM study, pulse width modulation, done using TAFE. Very common simulation package, used it many times. The 555, of course, has 2 comparators set up as a window comparator. You can see them both here. The high comparator, number 2, is set at 66% of the supply voltage, and the low comparator is set at 33% of the supply voltage. Quite easily shown in this nice diagram because 5K, 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 we've got a voltage divider whereby if we get 5K and we divide that by 15K and multiply it by VCC, we'll find that we do in fact get 33% of rail. And likewise, if we get 10K and divided by 15K, simple ratio there, multiplied by VCC, we'll get 66%. Now, one thing that we'll have a quick look at before we go too far here, I've done a diagram at the bottom showing the inverting input on, just say for example, a 741, because it didn't have to have a part number, but I allocated a part number to this one. All operational amplifiers or comparators are the same. They have a inverting input and they have a non-inverting input. In the non-inverting input, it's quite easy to work out how these things function, because we see if it goes more positive with respect to the negative, the output swings positive, the output from here. If it goes more negative with respect to the negative terminal, the output goes negative. But of course, when we look at the inverting input, we have to consider that now we've got, if we get a gross positive input here, we only needed about 50 microvolts difference between the 2 terminals if we consider this as a differential amplifier with a lot of gain. Open loop gain of a 741, say, is about 200,000 times. So about 50 microvolts more negative, and the output is going to swing positive because we have inverter action. If the input goes 50 microvolts compared to its buddy, more positive, then we get comparator action and we get inversion, we get the output going more negative. So these are the rules that I've set up here specifically for comparators and operational amplifiers used as comparators. Going back to our circuit, I've used a constant current generator in this circuit because I wanted to get a beautiful linear ramp occurring on the output. This is this linear ramp here. And normally when we charge a capacitor starts off charging, drawing a lot of current, and then as the voltage across the plates reaches the supply voltage, the current that the capacitor draws for the charge drops away to almost zero, and then finally is zero. But in this case, we don't want an exponential curve, which would normally happen in that case. I want a linear curve, so I've had to use a constant current feeding the capacitor, which does in fact result in a beautiful linear curve. And these ramp generators, sawtooth generators if you like, are used in many, many types of electronic equipment. I remember working with radar and oscilloscope circuits many years before, and dealing with some beautiful circuits set up for sawtooth waveforms. Even the deflection in CRT type televisions had to use a sawtooth waveform like this to get linear deflection on the screen. So what have we got happening? We've got the threshold input and the trigger input. Trigger is 33% of VCC, we saw earlier. Threshold is 66%. I've tied both of these together. Now, let's have a look at that. Here's trigger, number 1 comparator. Here's threshold, number 2 comparator. The high comparator, the low comparator. I've tied both of these pins together. Remember, I said these act as a window comparator with 2 thresholds, a high threshold and a low threshold. Each of these pins that are tied together now are coupled to the capacitor, and the capacitor is coupled back via a 10K resistor into this pin called discharge. What's this pin called discharge do? This pin called discharge is here, pin 7, and it's a NPN transistor. And when the NPN transistor base gets current fed to it, the transistor turns on and we get almost a short circuit between the emitter and the collector. So the 10K resistor coming in here, if that transistor turns on, will allow my little capacitor to discharge via that resistor to ground. Something has to happen, though, to trigger that cycle. Something has to happen here to turn this transistor on. And that happens with number 1 comparator. I've said here in the notes, low comparator for 33% switching. When the low comparator input goes 50 microvolts more negative than the input, which is 33% of rail voltage, then inverter action causes the output to go high to the set input of the flip-flop. Not Q becomes zero logic, i.e. 0 volts, and the base of the NPN transistor gets no base current, no base voltage. Therefore, the NPN transistor turns off, collector becomes a high impedance to ground, and the capacitor C1 can now begin charging again. That would be, by doing that, by turning that transistor off, it's like getting an axe and putting it through this wire. We no longer have a 10K current path coming down here to ground because the transistor switching there has been turned off. So now I've got a constant current source coming down here that I've set up with the BC557, and the capacitor can start charging linearly because of that constant current which is fed across the capacitor plates. The voltage across the capacitor starts charging then at this 33% of VCC, which was set by the bottom comparator. We saw earlier that threshold on the bottom comparator is 33% of rail. The capacitor starts charging, heads up towards 66%. On the graph here I've shown from Tina that 3.3 volts is the lower threshold, 6.6 is the higher. Cappy starts charging at 3.3, heads linearly up to 6.6, and then bingo, something happens here which then has to cause that transistor to discharge again. So let's have a look at that. This is this high comparator which causes the switching at 66%. When the high comparator positive input goes 50 microvolts more positive than the negative input, the output goes high to the reset input on the flip-flop. Here's my flip-flop built into the 555. Simple bit of logic happening here. And the reset goes high. If the reset goes high, then the not Q output will also go high. When the not Q output goes high, that puts current into the base on the NPN transistor, turning on the transistor, and then we get a very, very low resistance between the collector and the emitter, almost zero here, and the 10K resistor, which is connected to pin 7. Let's go back up and have a look. Here it is here. 10K resistor is again connected across the capacitor, causing the capacitor to discharge, and that will continue to discharge until the other comparator, comparator number 1, which switches at 33%, again sees its negative input because of pin 2 drop 50 microvolts below 33% of the rail supply, and then that will turn off the transistor, which causes the capacitor to start charging again. Now, we said that we had a beautiful linear current or linear voltage rise here because of the constant current source going into the capacitor. But what's happening when the capacitor discharges? I don't know if you can see clearly on this graph, but that is curved. I've exaggerated that now in another graph. I've blown this right up on Tina, and I've changed the horizontal dispersion on the screen to make now 6.6 volts here, 3.3 volts here. Really convenient to use the 10 volt rail on a 555, because then 66% equates to 6.6, 33% equates to 3.3. Capacitor discharging from 6.6 to 3.3. There you can see the actual discharge curve, and I've sketched in here with graphics using a nice linear line there, and you can see the divergence and the convergence at each end, showing that we definitely have an exponential fall as that capacitor discharges. The output from my circuit is taken across the capacitor. I have to ensure that the following stage uses quite a high impedance of input, so preferably I need a buffer or something following this. Otherwise, if I have too small a resistance on the following stage, that will again cause the capacitor to discharge, and it will disrupt the linear rise, and it would be adverse to what I'm trying to gain from the circuit. We'll have a look more at that in part 2 of this when we go on and look at the level shifting, and we look at the LM339 comparator in the final part of the circuit. Now, with all circuits like this, it's nice to do it in a simulator, but we should really build this up on the breadboard and test it. I've done that, and you can see now on the breadboard the 557 transistor. You can see the LM555 buried in the midst of the wires, and you can see the various resistors and capacitor there to make the circuit work. And then having a look at the oscilloscope waveform, well, this really does come back to the necessity, shows the necessity to do these tests in real live equipment, because look at the noise spikes. I've got noise spikes happening at the crossover points. I've got noise spikes happening where the linear ramp reaches 66% and where the discharge reaches 33%. So I'm going to have to look at that more closely and see what I can do about eliminating those noise spikes. This has been Greg Moore for New South Wales TAFE. Thank you.